Hello everyone, this is Miss Shearman. This is the third lesson for Year 10 Y band this week. We're going to be looking at radioactivity and its uses. So for 10Y1 and 2, this is revision. We will be doing a topic test on this when we're back in school. And for 10Y3, this will be new knowledge. For you. I am going to be going through it quite quickly as it's revision for most people, but obviously you can pause and go back over information whenever you need to. It would be helpful to have a pen and paper handy, or some way you can maybe type up notes or answers to questions if you want to. So today we're revising the different types of ionising radiation, so that's alpha, beta, gamma, and how they're used in cancer treatment. So we'll be looking at the properties of those. We'll be looking at the link between radiation and cancer, and then looking at how radiation can actually be used to treat cancer in the form of radiotherapy, and we'll also be recapping what we mean by chemotherapy. So there's a do now task on the screen if you'd like to pause and have a go at those questions. So I'll give you the answers to those questions now, so pause this if you haven't finished. The total number of protons and neutrons in the atoms of that element is the mass number. An isotope is a version of an element with a different number of neutrons. So for example, carbon can have a mass number of 11 or 12 or 13 or 14 because the number of neutrons in a carbon atom can be different. And the last question, the electromagnetic waves that can cause cancer are X-rays, ultraviolet rays and gamma rays. So these are the things we're covering today. The properties, as I said, of alpha, beta, gamma, the link to cancer, what we mean by half-life and how we can work that out from a graph, and cancer treatment. Electron is released from the nucleus, and gamma radiation is when we get a gamma wave or a gamma ray, also known as a photon, released from the unstable nucleus. So that's the three types of radiation. Now, different types of radiation have different penetrating powers. In other words, some are better than others at travelling through materials. If we start with alpha radiation at the top, alpha radiation is 2 protons, 2 neutrons. It's quite a big particle as radiation goes, and so alpha radiation can travel through air, but it's actually stopped by paper, and in fact it's stopped by skin as well. So alpha radiation is the least penetrating of those 3 types of radiation because it's absorbed and stopped by paper and skin, and in fact it can only travel a few centimetres through air. Beta radiation is more penetrating, in other words it can get through more stuff. So beta radiation can travel through paper, but it will be absorbed and therefore stopped by aluminium. Gamma radiation is the most penetrating. Gamma radiation can get through paper, through aluminium, and it will be slowed down by lead. So thick lead will absorb some gamma radiation, but often let small amounts through. It takes enormous thicknesses of lead or concrete to actually stop gamma radiation. We also need to think about the ionizing power of alpha, beta and gamma. So what do we mean by that? Well, they are forms of ionizing radiation. And what that means is that they can knock electrons off of atoms, causing damage. So when alpha, beta or gamma radiation are sort of fired at atoms, they can actually strip electrons off those atoms and change them into ions. That's what we mean by ionizing. Now, if this happens to the atoms that are in our DNA, in our cells, and ionizing radiation rips atoms from our DNA, it damages our DNA, and that can cause cancer. So ionizing radiation is a cause of cancer, but can also be used to treat cancer. We'll come on to that in a little while. You need to know which is most ionizing and which is least. So the order is alpha, beta, gamma. Alpha is the most ionizing. In other words, it's most able to strip electrons off of atoms, followed by beta, and then gamma is the least ionizing. Okay, so let's just check what we've learnt so far. Some true or false questions. Number 1, alpha particles are made up of 2 protons and 2 neutrons. Do you think that's true or false? Gamma radiation is the most penetrating form of radiation. Do you think that's true or false? And number 3, alpha radiation has the lowest ionizing power. I'll move on to the answers now. So number 1 and 2 are true. Number 3 is false. Alpha radiation has the strongest ionizing power, followed by beta and then gamma. So we've looked at the properties of alpha, beta and gamma radiation, and we've thought about the link to cancer. Ionizing radiation can damage our DNA and therefore cause cancer. Now let's think about half-life. So scientists can actually measure the amount of radioactive decay or radiation being given off by a radioactive material. So imagine you've got a piece of uranium, which is a radioactive metal. You can actually measure how much radiation is being given off. And over time, as more and more of the uranium decays, the amount of radiation given off will decrease. Now, the time it takes for the activity or radiation to halve is known as the half-life. So radioactive material with a long half-life takes longer to decay. And half-life values vary hugely. Some radioactive materials will decay so quickly that their half-life is a matter of seconds. Others will decay so slowly that their half-life can be millions of years. I'm showing you now what's called a half-life graph. So the graph is showing the amount of radioactivity remaining in a radioactive material over 8 years. And I'm going to talk you through how we can use the graph to work out what the half-life of that substance is. So you can see that at the start, at 0 years, there is 100% of radioactive material remaining. What we need to work out is how long it takes for the radioactive remaining percentage to halve. So it's 100 at the start, half of 100 is 50. What we want to know is how long has it taken for the activity to drop from 100 to 50. So half of 100 is 50. I come down to 50, I go across to my line of best fit and down to 1. The half-life of this sample is 1. So just to remind you, I always look at the highest number my line of best fit has got to at the start of the graph. I divide that by 2 to work out half of it. 100 divided by 2 is 50. I come down to 50, I go across to my line of best fit and down to my x-axis. And the answer is that my half-life is 1 year. I'm going to show you another graph now. See if you can work. What I've done is taken the activity at the start to be 70,000. Divided that by 2 to find half of 70,000, which would be 35,000. We then need to come down to where 35,000 would be on the graph, that's just here, come across to our line of best fit and down. And the half-life for this radioactive material is 6 hours. 6 hours. So we've now looked at the second part of our learning journey today. We've looked at what we mean by half-life. We've looked at a half-life graph to work out what the half-life of a substance is. And lastly, we're going to look at how we use radiotherapy and also chemotherapy to treat cancer. So remember, cancer is caused when cells are damaged. The DNA becomes damaged and so faulty cells are produced, and that's what we mean by cancer. So we can treat cancer using radiotherapy, which is radiation treatment, and chemotherapy, which are drugs. Both types of treatment destroy the cancerous cells, or aim to, but sometimes they can destroy healthy tissues too, and you may be aware that radiotherapy and chemotherapy can cause side effects which are not very nice. So let's start with chemotherapy. Chemotherapy is basically treatment using drugs. They're drugs that destroy cancer cells, and you either take them as a tablet or they can be injected straight into your vein. So you might have heard the term intravenous or IV drugs. That's what that means, being injected straight into a vein. The drugs are often really toxic because they've got to destroy nasty cells. But that can affect your healthy cells as well, and that's why chemotherapy can often make you feel quite unwell, and there are other side effects you can get from chemotherapy, such as losing your hair, for example. Radiotherapy is using ionized radiation. We know that if ionizing radiation damages DNA of healthy cells, it can cause cancer. But we can use that ionizing radiation to damage the DNA in cancer cells and hopefully kill them. As I mentioned, you can get side effects by damaging healthy cells too, though fortunately healthy cells tend to be damaged less by radiotherapy than the cancer cells, and doctors and radiotherapists are really careful that they only apply the radiation to the cancer rather than to the healthy tissue. And radiotherapy can be given from outside the body, so they sort of fire beams of radiation into the body at the tumour, or sometimes they will actually inject or place a piece of radioactive material inside the body or inside the tumour itself so that it damages the tumour cells and kills them. So just some things to think through. I'll go through the answers in a moment. For internal radiotherapy, so radiotherapy where we're putting a radioactive material directly into the body, would you want to use an isotope or radioactive material which has got a long half-life or a short half-life, which would be better to go in the body? And would you want a high penetrating power or a low penetrating power? And then once you've thought about that, think about what you would want to use for external radiotherapy. Radiotherapy where we're applying radiation from outside of the body. You may want to pause this now and have a think. Okay, I'm going to go through the sorts of things you need to be thinking of now. These are quite common questions in tests and exams. So if you're going to put, let's start with internal, if you're going to put a radioactive material inside the body, you don't want it to be radioactive for years and years and years and years and years if it's going to be inside the body. So we would choose a radioactive isotope with a short half-life. probably of a few hours or a couple of days, so that it has time to work on the cancer cells, but then it becomes much less harmful. And in terms of the penetrating power, well, you would probably want a radioactive source that didn't penetrate very far, so that the radiation is really just targeting the tumour that the radioactive material has been put inside and isn't able to spread out around the body. And for external radiotherapy, well, external radiotherapy is actually given over a period of several days or weeks usually. So we'd actually want a radioactive isotope with a long half-life so that it lasts and we can use it repeatedly to fire radiation at the patient. And it would need to have a high-ish penetrating power. It's got to be able to penetrate through the skin and through the body's tissues and arrive at the tumour site. So we would want a higher penetrating power. Okay, we've now covered the 3 parts of the lesson that we set out to cover today. What you could do now is go back over any of the information I've covered that didn't quite make sense, or you could go to the Word document that I have added to this assignment, which actually contains some links to some really good videos on from a website, a YouTube channel rather, called freesciencelessons.com. They are based on the English science specification, but it's pretty similar to the Welsh one. And there are some really helpful videos on ionizing radiation and half-life. And then a couple of videos from cancer charities about chemotherapy and radiotherapy that you might find useful. Okay, you can submit your work to me by taking photos of your notes and handing them in, or if you've done something electronically, you can email that or add that to the team's assignment. Okay, cheers guys.